Welcome back, ladies and gentlemen. We are on Quadratic Basics Day 5, Word Problems and Graphing Notes. Now, there are three main forms of quadratic functions. Each form requires a different strategy for graphing and evaluating the key features of the function. There's standard form, which is y equals ax squared plus bx plus c. Vertex form is y equals a times the quantity x minus h squared plus k. And intercept form, which is also known as factored form, which is y equals a times the quantity x minus p times x minus q. Now, when you're finding the vertex in standard form, there's a formula that we use. The x-coordinate is equal to the opposite of our b coefficient divided by 2 times our a coefficient. Remember, the coefficient is the number found in front of the variable. Once you've found the x-coordinate, then you can substitute that into the equation and solve for the y-coordinate, which is why I'm saying plug in x. The roots for a standard form, in other words, the x-intercepts, are found when you're solving for x using y equals 0 because x-intercepts always have a y-coordinate of 0 to be on the x-axis. And you can do this by factoring using quadratic formula or completing the square. For y-intercepts, you can actually pull that directly from the standard form of the equation. The constant at the end of the equation, in other words, the number without the variable, is the y-coordinate of your y-intercept, because if you substitute 0 in place of x in the other two terms, they actually zero out of the problem, and you're left with y equals c. And this is actually the only form of the equation where you can find the y-intercept directly from the equation. Now, if you want to change forms, if you don't want to stay in standard form, to go from standard form to vertex form, we would use completing the square like we did for solving in one of our previous videos. If we want to go from standard form to intercept form, then we would factor, which is also why the intercept form is called factored form. Now, why would we want to change to any of these other forms? Well, vertex form is called that because you can pull the vertex directly out of the equation itself. And when you're finding the vertex, notice that in the equation, we have x minus h, which means that however this shows up in the parentheses, it's going to be the opposite of whatever h was when it was plugged in. That's why we tend to take the opposite of whatever number is next to x as our x-coordinate of our vertex. And then notice that k has a plus sign in front of it. We've already taken the opposite by adding it to the other side, so you can actually just take k directly from the end of the equation as is. Now, the roots, again, the x-intercepts, we're solving using y equals 0. And if you put 0 in place of y here, all you would need to do is subtract the k to the other side, divide by a, take your square root, and then add h. Basically the same solving steps that we would do after we completed the square if we were completing the square from standard form. Here we would complete the square first to get vertex form or be given vertex form, and then do the solving steps necessary to actually find our roots. Now, finding the y-intercept, remember, every y-intercept has an x value of 0. So put 0 in place of x and actually find what y equals. Now, changing forms. To go from vertex form to standard form, you just simplify the function. You would multiply out the x minus h quantity squared using distributive property, multiply a into what you get from that distribution, and then add k at the end. Now, vertex form to intercept form is a little bit more complicated. Usually when we're in one of these more specialized forms, we stick with it. Because to go from vertex to intercept form, you would have to first change from vertex form to standard form, and then factor. Frankly, that's a lot of work. We don't often put in that amount of work unless we absolutely have to. For the intercept, in other words, factored form, we can find the vertex by using the concept of symmetry. Every single parabola is perfectly symmetric through the vertex, which means that our x-intercepts, which have the same value of y, being 0, are equidistant from our line of symmetry. So all we have to do to find our vertex is average our x-intercepts. In other words, using midpoint formula, just adding the two intercepts and dividing by 2. And once you know that x-coordinate, you can put that into your equation and solve for y. For the roots, the x-intercepts, that's the usefulness of this form, is that we can pull them directly from the factored form. Basically, just set each of your parentheses equal to 0 and solve, and you'll have your roots. Now, for the y-intercept, we have to put 0 in place of x and then simplify the problem. Now, if we want to change forms, if we don't want to stay in intercept form and we want to go to standard form, then we simply use our distributive property and simplify. Now to go from intercept form to vertex form, it's just as complex as going from vertex to intercept. We would have to change the standard form first and then complete the square. Now, there's one other thing that I want to mention before we get into the main examples of this lesson. And it's an interesting pattern that we find when graphing the parent function. So the parent function of all of these is y equals x squared. That is the most basic version of a quadratic. And the thing that I want you to notice is not the fact that all of these x's are actually squared, giving you squared numbers for y, it's the difference between these, the change in them. Now, linear change stays consistent, but once you get beyond linear, then you have different kinds of changes, and there's actually a pattern within these changes. If I want to go from my vertex to my first coordinate beyond the vertex, that is a change of 1. If I want to go from that first point beyond the vertex to the second, that's a change of 3. To the third point, it's a change of 5. Now, what I want you to notice about these numbers is that this is a very specific number set that I'm starting to write out. 1, 3, 5 is the beginning of the odd number set. And if we want to keep going, from 9 to 16 is a change of 7. If I wanted to figure out the next coordinate, I would just change by 9, and then by 11, and then 13, and then 15, and so on. So you can use these odd number changes to help you figure out what your next point is when you're graphing without actually calculating it. When I graph these, I look for where my vertex is, in this case 0, 0. And then when I go one coordinate, basically one change of x out on either side of this, if I have a positive in front of my x squared, in other words, if my a coefficient is positive, then I'm going to increase by 1 as I go out 1. Then increase by 3 as I go out 1 more, and then increase by 5 as I go out 1 more. And you end up with the points of your parabola. So if I didn't have this table off to the side and didn't feel like calculating all the coordinates, as long as I had my vertex and I knew this pattern, I could graph this very quickly, actually faster than you could with a calculator. And so we're going to be applying that pattern here in just a few. First, I want to go over how to switch from standard form to vertex form using completing the square. All right, now, when I'm going into vertex form for completing the square, we could use the actual square, which I'll show up here. The x squared goes in the top here. This 16x, to be a square, we have to have equal sides, which means that this middle term has to split equally. In other words, divide it by 2. That leaves me with an 8x here and an 8x here. Now, x squared can only split into x times x, which means I need x times 8 to get 8x, and I need x times 8 down here to get 8x. This leaves me with my completed sides, and 8 times 8 would give me this thing right here, which is what I need after that 16x to make this a perfect square trinomial. And that perfect square trinomial of x squared plus 16x plus 64 would simplify down to x plus 8 times x plus 8, which can be rewritten as x plus 8 quantity squared. Now, when I'm adding this 64, I need to add it to both sides. And this 71 is just going to kind of hang around for a minute. Now, I'm going to keep the y plus 64 as is for the current moment. I'll fix that here in a minute. And this x squared plus 16x plus 64, as I said, is the equivalent of x plus 8 quantity squared, because we have an x plus 8 on the left and an x plus 8 at the top when I completed my square. So I can rewrite all three of those terms as x plus 8 quantity squared and leave the plus 71 at the end. Now, when you look at vertex form, it's y equals, not y minus k. The minus k was already added to the other side. So I need to get just y equals to have this fully in vertex form to be able to pull my vertex from this equation. So I need to get rid of this plus 64, which is the thing that's keeping me from having y equals. So minus 64 on both sides. And now I have y equals x plus 8 quantity squared plus, let's see, 71 minus 64 leaves me with 7. Now something else to keep in mind. Our generic form of vertex form is y equals a stretch factor of a times x minus h squared plus k. Originally, the k would have been subtracted from the y, similar to how we set things up with point slope form with linear equations. But with this form, we've already added the k to the other side. We've already taken its opposite. So this 7 right here is already our k for our y coordinate. Now our x coordinate, this has a minus h right here. So whatever we see here, please excuse the bell. Whatever we see here, we need to take the opposite of it. So the opposite of plus 8 is negative 8. And the reason this works is that if we were to put negative 8 in place of h, minus a negative turns into plus a positive, which is where that plus sign actually came from when it was originally supposed to be a negative. So the general rule of thumb is that whenever the coordinate that you're pulling from the equation is next to its variable, you need to take the opposite of that coordinate because there is a minus sign in the original form. Whenever that coordinate is already on the opposite side of the equal sign from that variable, we've already taken the opposite of that number so that you can just take the number with the sign it already has. So that's why I had to take the opposite of the 8 and then the positive 7 as is. I'm going to go ahead and do just one more of these. And I'm going to simplify these steps. Over here, I had to take my 16 and cut it in half, which gave me 8. And when I squared that, because it would have been times itself in that perfect square, I got the 64 that I needed to add to both sides. So I'm just going to use a simplified version of those steps. My negative 2 is what I need to cut in half this time because that's the number in front of x. That gives me negative 1. Now when I square negative 1, I get positive 1. So I need to add 1 to both sides in order to have my perfect square trinomial. And so this is the part that I was adding on both sides. My minus 5 is just kind of coming along for the ride. Now that y plus 1 would be set equal to x and then minus 1 quantity squared. The reason I know that this is a minus 1 is that your middle term that got cut in half produces the coefficient that goes in front of x in our perfect square. It's also the number that gets pulled out to the sides to become the second term in our binomial that's being squared. Right, so here this 8 became the plus 8 inside of here. Over here this minus 1 or negative 1 is becoming the minus 1 at the end here. And everything else around it just stayed the same. Now I do need to subtract this 1 to the other side, so I have y equals on its own. And I have y equals the quantity x minus 1 squared, and then minus 6. Now when I pull my vertex from this, remember it's the opposite of whatever's next to the x, so in this case positive 1. And then the same as whatever's at the end because this had a plus sign while that had a negative sign. This is telling you to take the opposite of what you see. This is telling you to take the same as what you see. All right, let's go on to how to graph these. So now that we've practiced transforming equations into vertex form, let's take something in vertex form, pull the vertex, and talk about the axis of symmetry. So the vertex for this equation would be the opposite of whatever's next to x. So in this case, we have minus 2, so I need to use a positive 2. My hand got ahead of me there. And then we use the same as whatever's after this because we've already taken the opposite. Now the axis of symmetry is the vertical line. There we go. There's our vertex. The axis of symmetry is a vertical line through the through the vertex. Now vertical lines have a constant change in y, basically an infinite change in y, but our x's stay the same, which is why they're defined by their x value. In this equation, every single x value is equal to 2. So the axis of symmetry is always x equals the x coordinate from your vertex. And it's important to note your axis of symmetry because this is how we're going to graph the rest of this equation. Now notice that there would be a 1 in front of those parentheses if we were to write it in. And that means that our stretch factor is a positive 1. So the pattern that I showed you over on this side, where each of our points, as they extend from the vertex, increases by the odd number set. So since I have my vertex right here and I have a positive stretch value of 1, I'm going to increase by 1 as I go to the right one. And I can repeat that on the left because it's symmetric, so it folds perfectly onto itself. And from that point, I need to increase by the next odd number. So after 1 is 3, so 1, 2, 3, as I move outward from my axis of symmetry by 1 on either side. And after 3 would be 5, so 1, 2, 3, 4, 5. Next would be 7, 1, 2, 3, 4, 5, 6, 7. And I have my parabola sketched without even having to use a table or a calculator to figure out what the values of these points are, just by using the pattern that exists within the parabola. Now, if this had had like a 2 in front of it, then I would have used double those changes. So I would have increased by 2, by 6, by 10, by 14. If I had had a 3 in front of here, I would have tripled my pattern. If I had a negative, like I do down here, then instead of this opening up, it'll open down and my change will be decreasing by that instead of increasing by that. Now, once I have my graph here, I can actually find my x-intercepts very quickly. Right, so my first x-intercept is at the origin, 0, 0. My next one is at, let's see, 1, 2, 3, 4, 4, 0. Don't forget to write these as points. My y-intercept is also at 0, 0. And I have all of my key features and I have my graph. I'm going to do the same thing for number 4, but this time I have this negative sign in front, which means I still have a stretch factor of 1, but it's a negative 1, which means that this thing is actually flipped over the x-axis. Well, not really over the x-axis. It'll be flipped down instead of up from where the vertex is. So let's find our vertex first. So we have x plus 1, so I'm going to use negative 1 because I need the opposite of whatever is next to the x. In our generic formula, this had a plus sign, so I need to use the same sign as is there. So positive 9. My axis of symmetry will go through x equals negative 1. So I'm going to the left one and then up 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to draw my axis of symmetry. And now I need to open downwards, but I'm still going to use that same pattern because this is times a negative 1. If it were times negative 2, then I would double my pattern and so on, like I mentioned in the previous graph. So from my vertex point here, as I go outwards 1 from that vertex, I'm going to go down 1 this time, and then I'm going to go down 3. And it's always moving from the previous point. Then I'm going to move down 5 on either side. Then I'm going to move down 7. And if I had more space, I would move down 9 as well. And this provides the graph of my parabola. And again, makes it much easier for me to find my key features without having to do the solving steps I mentioned in the table on the other side. If any of these key features are more difficult to see from the graph, then use the solving steps that I mentioned in the table to actually be able to solve for them directly. Now, x-intercepts, again, where the graph crosses the x-axis. So this one's crossing at, let's see, 1, 2, 3, 4, negative 4, comma 0, and then at 2, comma 0. And my y-intercept is at 1, 2, 3, 4, 5, 6, 7, 8. Oops. So 0, comma 8. And this is why vertex form is actually very useful to us. Now, what if it's not in vertex form? What if it's in standard form instead? All right, so using this equation, y equals negative x squared plus 6x minus 5, complete the table, graph the parabola, and identify its key features. Now again, if any of these key features are harder to find once we've graphed, then you'll want to use the solving steps in the table to be able to find them. Now, first things first, I want to get my vertex again. And I could use completing the square if I wanted to, but I'm actually going to use the formula for this. So the x-coordinate of the vertex is negative b divided by 2a. Now, just a reminder, the generic form for this equation is y equals ax squared plus bx plus c, which means that b is the coefficient in front of x, so b is 6, and my a is the coefficient in front of x squared, and if there's no number there, it's automatically a 1, but there is a negative sign, so this would be a negative 1. And I'm going to go ahead and put these numbers in here. So I have negative times 6 over 2 times negative 1. Now, just a reminder, this is a lowercase letter b, and this is the number 6. Now this gives me negative 6 over negative 2, which is positive 3. Once you have the x-coordinate for your vertex, you can substitute into the equation to find the y-coordinate. Oops, it should be minus 5. Let's see, 3 squared is 9, so I'd have negative 9 plus 18 minus 5. And I could just type this into the calculator exactly as it appears, without the y equals, and calculate this directly, but I'm just going to go ahead and work through this in my head. So negative 9 plus 18 gives me 9, minus 5 is 4. And your vertex should be in the middle of your table, just like it's in the middle of your graph. And so I'm going to count down 1, 2, 3, 4, 5, 6, 7 points available. So 1, 2, 3, 4. I'm going to put the 3 here, 4 here, and this helps me figure out what numbers I should put into my table if I want to use that to graph this. Or I can go ahead and use my pattern and fill in the table later. Whichever way you want to do this is fine. I'm going to go ahead and use my pattern so I can show you how to use this with standard form. So my vertex is at, let's see, 1, 2, 3, and then up 1, 2, 3, 4. My axis of symmetry is going to be the vertical line through this, so I can already write down my vertex as 3, 4, and my line of symmetry as x equals 3. Now, from this point, because I have a negative a, I have a negative stretch factor. Now, the stretch factor is still 1, so I'm not going to have to double my pattern or anything like that, but I do have to invert it, so instead of increasing by odd numbers, I'm going to decrease by odd numbers. So when I go out 1 on either side, I need to go down 1 first. When I go out 1 more on either side, I need to go down 3. Going out 1 more, I need to go down 5. And if I have room, I would go down 7. I think this is sufficient. It's enough to get your sketch on the graph. Now my x-intercepts are where this is crossing the x-axis. It's crossing at negative 1 when y is 0, and it's crossing at, let's see, 1, 2, 3, 4, 5. Whoops, that was a positive 1, my bad. So 1, 2, 3, 4, 5, 5, 0. For the y-intercept, we're going to be down at 1, 2, 3, 4, 5, so 0, negative 5. And if we want to, we can go ahead and fill this in. So I started up at 4, I went down 1, so I was now at 3. When I went down 3, I ended up at 0, and when I went down 5, I ended up at negative 5 for each of those.